last class, the last thing said, remember this, using the spectral decomposition theorem, you can write a symmetric second order tensor in this way. Or this dot product between these spaces, these are the principal directions. We called it MA. And these are the principal stresses. Referring to the shear stress, which is a second order tensor, symmetric second order. So now we're going to talk a little bit about the rotation of the principal direction NA. So let's define the vector uppercase NA belonging to R3, and where the norm of this vector is equal to 1, so it is a unitary vector. And let's define NA, lowercase a, in terms of this vector as some matrix or tensor Q times NA. So where this is a rotation matrix. Right, we can do that. So that means that one characteristic, one feature of this basis was that these are, with respect to each other, are orthogonal, right? And these guys are real. Remember that? So these bases are orthogonal and these guys are real. So let's say that these are N1, N2, and N3. So here we're saying that we can obtain this basis by rotating a different set of bases, basically. So for instance, you have here N2, let's make N1. Something like that. We're rotating the basis by applying this rotation matrix. Q. And you may already know that Q times Q transpose is equal to the identity, right? Which implies, right, that Q transpose is equal to Q inverse. Right? So these are orthogonal matrices. And these orthogonal matrices belong in 3D to what family? SO3. Exactly. So they belong to the group SO3, which is the special orthogonal group in 3 dimensions. SO3. Now, we can also use this to take the time derivative. So from that we know that Q times Q transpose, the time derivative, must be equal to 0, right? Because the identity here is just a constant. And taking the time derivative, we have Q dot times Q transpose, right? Plus Q times Q transpose dot. Where this product here is called omega. Which is also called the spin tensor. And this is minus omega transpose. So omega transpose is minus omega, which means this is plus 0, yeah, which means these are skew symmetric. Right? These are skew symmetric junctures. Now, let the NAs depend on time. How? Such a way that NA dot is equal to Q dot times NA. Right? And we have also this definition here. And from here we can rewrite this one. This one is equal to Q dot times NA is Q transpose, right? Q transpose times NA, sorry, lowercase NA, right? But this guy here is omega. So this one is equal to omega times NA. So that's interesting. If I want to get the time derivative of this guy, the only thing that I have to do is apply this spin tensor to that guy. That sounds somehow familiar. So this is kind of a differential operator, right? A finite dimensional differential operator. So that means that we can write this NA in this form, right? This omega is this guy. Where in operator theory, this is called the infinitesimal generator. And this belongs to a subgroup of bounded linear operators. So now using this definition, can try to write to obtain the time derivative of sigma in principal basis. So sigma dot is going to be equal to this summation times sigma A dot M A plus sigma A times NA dot diet NA plus NA diet NA dot. Right?
I have a question.
Mm-hmm.
When we take the time derivative there, why are we not using the product rule?
The product rule, what do you mean the product rule?
Like, we know NA is Q times NA.
NA?
Little NA is Q times capital NA.
Uh-huh.
So when we take the time derivative, why are we keeping only that term?
Why are we this?
Yeah.
This is what you mean?
Yeah.
Because we're defining this to be like that, right? So we have the basis originally here, right? And we're saying that how they change in time with respect to the rotations depends only on the rotation itself. So the angle of rotation is changing in time, but the original basis that in this case will be the uppercase n will still be the same basis. They aren't changing. They are fixed. And we're making it rotate in time from an original configuration to a given configuration depending on time.
So did you mean to say that NA don't...
Should there be independent of time?
Yeah.
No.
Yeah.
Just do the other way, right? So now let's compute NA. It's Q dot, right? Transpose times NA. Like that. See what I mean? But you can consider them fixed, and the only thing that you're changing in time is the rotation. You're rotating. The only one that is evolving is this Q. You can fix the original ones. You can also move it in a more general framework. Any other questions? So here we have this NA dot, which is is defined like that. So replacing it, we can rewrite this as here is omega dotted NA times NA plus NA that omega dot NA. And finally, we can write the sigma dot in this form. Follow why? Now from this definition, we can also see that this spin tensor can be written in this way. Right? Which is also equal to minus questions. No questions. Now let's consider a new second order tensor belonging to this set S. Remember what that set S was? Last class, the set of all the symmetric second order tensors. And why it is a set and not a group? Why it cannot be a group? It has to be only a set. Set of the symmetric second order tensor. Yeah. We have identity, right? We have an operation, this dot product between the two. But these guys aren't always invertible. So that's why they don't form a group, and they have to stay as a set and not a group. So we can write this phi in the same way, right? Using the spectral decomposition theorem. And therefore, we can write the derivative, the time derivative of this in the same fashion as before. Now, what if we hit this guy with the spin tensor? What do we get? So the spin tensor, as we defined, we just defined here. They're written that way. So here we have sum equal to 1, 2, 3 NA dot diet NA. And this guy is the sum B 1, 2, 3, sigma b, m, let's write it this way, m b diet m b. Right. We can write it what is this?
Sure.
What if A is equal to B?
1, 4,
So what is this?
delta AB.
This is delta AB. Right. So this is nothing but 3 Right. So we're extracting or projecting this phi onto this skew-symmetric spin tensor, and that extracts the principal, well, the eigenvalues of this symmetric tensor, projected on the skew-symmetric part. We can also extract the components of this spin tensor in the principal basis, right? In A and B. And what is this? By definition. The derivative of this side, right? This is m dot b. So we have this dot product, which is just a number, omega AB. Now this omega AB is equal to 0 if A is equal to B. Right? It shows like the pseudo tensor, the Levi-Civita permutation symbol, right? When I equals to j equal to k, this is 0. If we have an even permutation, this is positive, right? That's 1. And we have an odd permutation, this is negative. So this is shows like that, but instead of 3 indices, just 2. This is also AB positive, BA negative, and A equals to B equal to 0. So we can write this omega spin tensor in principal basis just like the matrix representation of this would be 0, 0, 0 here. We have omega 1, 2, omega 1, 3, minus omega 1, 2, omega 2, 3, minus omega, this is minus omega 2, 3, minus omega 1, 3. Just like this. Is that right? So that's why we can pack these guys in quaternions. And then read this experiment in that field. Ask him if you want to know more on the rotations and the quaternions. So this also gives us this way of writing it in principal basis, this compact way. Then we have here another way of writing this spin tensor. Now let's do the same exercise as before. Let's hit with this guy, this other one. So omega times phi is equal to this. Times is that right? And now we can rewrite this in this way. That's it. What is this? Once again, delta BC. And then we have that omega times phi is equal to call this product MAB. And one more way of writing. So now let's convert this to that. To that one there. So this guy is this one, right? And A. So, and this one should be so this one is this one, or this one, that's it. And then we have this guy acting on this, which gives us this time derivative. Right? It's all the same. We're writing the same thing in different ways. So they should make sense. Questions?
A question, should there be
B, D, why D? Where's that D? A, B, and C. A, B, from here. A, B, C.
It's a don't BC though, because
Yeah, in the box.
BC, so
Because what?
You're
Chrono
choosing
delta.
BC, so you crop that delta BC into the.
Oh, no, yeah, but I'm just rewriting it.
Yeah, if you rewrite.
Yeah,
it,
I mean, I can
right?
yeah, I could have used B instead of, you
Yeah.
mean B.
Yeah, so if in
Yeah,
either case,
I mean,
there'd be
just
B
like
here.
change that one for the other one. It's the same, right?
I think
There
we
is-
will
there's
say
somewhere
Yeah, but there should be
cannot-
phi B. in that case.
There's no C, is what he's saying.
Yeah, the phi C in the box.
You're
No, in the box.
in the box.
Yeah, there should
There's
be
no
phi
fee C.
Oh,
There should be-
oh,
Yeah, that's what I'm saying.
Thanks. Yeah, that's true.
And why is it not different from A?
Why is it not different from
A.
A
Like, why do we not have B different from A?
here?
Yeah.
Oh, because we already defined, well, it's just a way of writing it. I mean, we already defined this number to be equal to 0 if A is equal to B, right? We can write it just like that. It's equivalent.
Ah, okay.
It's just equivalent. It's just a way of writing.
Right.
So now we can remember that sigma in principal basis had the form sigma 1, sigma 2, sigma 3. Right? And here 0, 0. So which implies that sigma dot in matrix form is going to be using these expressions that we were deriving before. Sigma 1 dot here, sigma 2 dot here, and sigma 3 dot here. And because of this guy, here we have omega 1, 2, sigma 2 minus sigma 1. Omega 1, 2. And here we have omega 1, 3, sigma 3 minus sigma 1. Right? So that's omega 2, 3, sigma 3 minus sigma 2. And so on. Which in a more compact way, in compact notation, can be written as just similarly as before. Or this is the material rate and this is the spin.
Is this sigma 3 minus sigma 2?
Minus. Thanks. So this part is giving you how the length is of this principal stresses is changing in time. And this part is giving you how these principal directions are rotating. If you will, the radial part and the rotational part. How they change in length and how they rotate. Any other questions? No? Now let's talk about the same thing but related to Hooke's law. So remember that Hooke's law can be written in this way in general, where this CE four-order tensor is kappa times PV plus 2 mu times PD. Right. Just to recall, this PV is equal to the volumetric projection. How do we compute that? Right? And this is how? What is this? This is the four-order symmetric identity minus right? Just to remember. Yeah, but even for general elastic materials, including hyperelasticity, we have that sigma is the derivative of this thing called the strain energy with respect to the elastic strain, right? So, for instance, for linear elasticity, what is this strain energy? One over two.
That's not
This one, right? That's the strain energy for linear elasticity. That's it. So now let's assume that elastic strain also belongs, and in fact it does, to the same set as sigma. So let's assume that this belongs to this set of symmetric second order terms. So if that is the case, I can write the spectral decomposition of this guy, right? With its own basis. And we want to compute sigma from that. So as we just wrote, sigma is the derivative of the strain energy with respect to the elastic strain, and this is equal to this derivative of the strain energy with respect to the eigenvalues of the strain, the elastic strain, using the chain rule, times these eigenvalues with respect to the elastic strain. Right? But using the definition here, this derivative is equal to what? Just by taking a look at this expression. It should be right? So we have that sigma is equal to this summation of the derivatives of the strain energy with respect to the principal strains, elastic strains, times these bases MA. It also can be shown that sigma A, the principal stresses, are equal to these derivatives here. And then we have that sigma is equal to A 1 to 3 summation of sigma A's times this MA's wiggle. But we know that this is also equal to the same summation sigma A MA. So hence we have that these two guys are equal, and therefore sigma and the elastic strain are coaxial. So if that is the case, the time derivative of the elastic strain can also be expressed as the time derivative of sigma, as before, right? In the same basis as sigma. Questions? So in the same way, Ogden, in 1984, showed by expansion that this four-order tensor, elastic moduli, which is equal to sigma with respect to epsilon elastic. So that implies that this is the second derivative of the string energy. Right? That's true. Can be expressed in the principal basis in the following way. little expression. So we can compute this. That way. So what if we have this case? What for that case? What do you guys think we should do for that case? That's a way of computing the components of the tensor for that case. Calculus 1, there's a way of going around this. So, use that one for that case. Now we can also give this guy a name, a simpler name. AB. For these AB coefficients, AAB elastic, are nothing but these these matrix. You guys know what these are, these lambda constants. Questions? Easy, simple.
So when you say use the tensor, like what exactly do you mean by that?
To compute those values. Because what happens if this is equal to that? Here, it blows up, right? But there is a limit. So you have to compute the limit when this one tends to that one. That limit. So in that case, computing that limit, we can use it. So-called L'Hopital's rule. And that's general for other cases. So this is for only the elastic modeling. But for tangent operators and things like that, that can be derived in this way. And in fact, they are derived in this way. So this is the way of going around that problem. More questions? So this is the difference between knowing plasticity and knowing Tresca. Sometimes you ask, you know plasticity? Yes, I know Tresca. They say, It's one thing is knowing Tresca, but another thing is knowing the whole framework of plasticity, which isn't as difficult, but isn't as easy as well. If you guys don't have any more questions, that's it for today.